And went further to conjecture, I have it written down, excellent, that this density would be a rational multiple of what's called Artin's constant, which is this alternating sum. And this alternating sum is sort of key to understanding what's going on with the proof. And there's an Euler factorization of this. Is this chalkboard? Mostly legible. So this is up to rational multiple, effective rational multiple, the density of these primes. And this was proven, so this conjecture came out, I don't know when, but this was proven by Hooley in 1967. I think he got a field no for this. No? Okay.
What does it mean, up to a rational multiple?
I mean, what happens is there's a finite number of primes where this is sort of the wrong local constant. You're counting extensions, and the primes which are bad have to do with something related to A, but there's only a finite number of them, and so you just have to change this by a rational number for finitely many primes, and you can effectively compute this. So it changes for each A, but only by a computable rational constant. Yes?
So what notion of density are you using? Maybe it doesn't matter.
The notion of density is the limit as x goes to infinity of p less than or equal to x, such that A is a primitive root mod p divided by p less than or equal to x. And by p I mean prime. So this exists is part of the conjecture. That you don't have to do anything with zeta functions or otherwise to talk about a density.
Cool.
Okay, and so proven by Hooley, but you have to assume GRH. Okay.
And isn't this known without GRH for like all but one value A?
Really?
Yeah, there was this series of papers proving it with some exceptions, and I think they still don't know a single A for which it's true, but they know that there's at most one A for which it's false. Keith Brown had the final paper on that.
That's brilliant. I haven't.
I hope I'm not missing a hypothesis, but I think that.
I'll have to look that up. I didn't know about that. Oh, apparently this conjecture was 1927 in a conversation with Helmut Hasse. All right. So, more questions? All right. Oh, yes.
Is there, maybe I should ask this later, but is there like some sort of simpler argument than the proof that he gives that there's infinitely many? As opposed to like a positive, some.
I don't know of any proof that any specific number is a primitive root for infinitely many. I don't know that that's known, but yeah. So the sketch of the proof. So let me just sketch this. So the idea. Actually, before I do that, let me do a motivating example. All right. So So what I want to show is part of this example is to see why it can be divisible by a square, and this would still be okay. So let's look at A is equal to 8. And you might think because it's divisible by a square, somehow this is going to be a problem, that there's going to be no things where it's a primitive root. But let's look at P11 and see what happens. So it turns out 2 is a primitive root mod 11, and we can look at the generators. We can look at sort of the orbit of 2, products of 2. So we have 2, 4, 8. Let me write this 2 squared, 2 cubed. 16 is 5. 10. And now you'll notice you have -1, so after that everything's just sort of the negative of itself. So -2 is 9, 6, 9, 7, 3, 6, 1. And the point is, this is a group of order 10. And they're cyclic. The multiplicative group mod P is cyclic. And so this is a degree 10 cyclic group. And here's our generator. What really matters, that ends up mattering, is the exponent. If it's an even power, it's clearly not going to generate the group mod 10. If it's a fifth power, it's not going to generate the group mod 10. It's going to generate something of size 2. But anything else is okay. Even something of order 4. No. But anything that's not divisible by 2 or 4.
5?
2 or 5 is going to generate the whole group.
Relatively prime to the...
Relatively prime to the... That's right. Relatively prime to the...
multiplicative order of the multiplicative group.
That's right. And so the point is, 3 is just great. And this idea of divisibility by a prime which divides the order is what motivates the proof. Does this make sense? So 8 is a primitive root. So the idea of the proof is that you want to, so we're going to have this set. By the way, reading Hooley's paper is, I guess it was written in the 60s, but it reads sort of like a 19th century British paper in that he uses words like shoe with an E and Dexter side of the equation. It's sort of amusing to read. I don't really recommend reading it, though. I'd recommend reading, actually I'd recommend reading this paper that most of this talk is from, which is by Hans Roscom, if you're interested. He does a much better expository version of this concept. All right, so we're looking for the set P prime, where A is a primitive root, mod P. And the idea is, assume A is not a primitive root. Well, what happens? It has to be a power of a primitive root. In particular, it has to be a power which divides P minus 1. It has to be a square, it has to be a fifth power in this case. In general, there exists a prime L such that A is an L power. This is talking about the exponent, and it'll generate a smaller group. And so T, so if we define TL is the set of primes P such that there's no obstruction at the prime L, such that L does not divide the index, meaning A is, well, let me write it 2 ways. L does not divide the index of the full multiplicative group over the group generated by A, or another way of writing this, A is not an Lth power, mod P. Then T just becomes this intersection. If there's no obstruction at any prime, then there's no obstruction. Then it's a generator. Julian?
Well, I mean, so with this, I guess just with this other part, this A is not being an Lth power mod P.
Yes.
I mean, so like if L does not divide P minus 1, then I mean, like A could still be an Lth power.
You're right. So I guess that I have to also assume L divides P minus 1 to make this equivalent. You're right. For it to matter. Otherwise everything has a unique Lth root. Other questions? Okay. So from here, so this is the first realization in Hooley's proof, is that you can realize whether or not something is primitive root based on whether it's a power of something. The next 2 steps are